Hello, my name's Stefan, and today I'm going to introduce you to maximum likelihood estimation, or MLE, as we nerds like to call it. The general setup in basic statistics, and certainly for MLE, is we have some data, we have a probability model that we think roughly describes that data, and we want to find the best estimate we can get of the parameter of that probability model. So if we're working with a Bernoulli trial, then we want to estimate what the probability of success on an individual trial is going to be. If we're working with a random variable that's exponentially distributed, we want to estimate the rate of that random variable, that sort of thing. So to begin with, once we've established a model for our data that we have, what we usually do is we start looking at the probability mass function or probability density function. The reason for this is because the probability mass function or probability density function will tell you roughly how likely a particular value is in comparison to other values. As a matter of fact, it's not roughly, it's pretty exact. So the reason why I'm using this sort of somewhat fluffy word of how likely the particular value is because I'm trying to encompass both discrete random variables and continuous random variables. For discrete random variables, obviously we have the probability mass function that tells us exact probabilities. So if you're rolling a die, the PMF for the experiment that is rolling a die will tell you, hey, the probability of getting a 1 is exactly a sixth. For probability density functions, so continuous random variables, you can't get an exact probability for a particular value. Say, if you've got a normally distributed random variable, you can't get a probability that you'll get x equals 1. But you can get probabilities for regions, and that's how we work with continuous random variables. But in the case of maximum likelihood estimation, we don't actually need to work with probabilities. We just need a relative sense of which values are more likely and less likely. And so that's why we use the word likelihood here. So let's have a look at an example. Bernoulli random variables are pretty straightforward. It's just, your coin flip type thing. And let's set it up by saying, okay, we have n observations of a potentially biased coin flip. So we're going to call each trial its own, we're going to give each trial its own random variable. So we'll have x1, x2, all the way up to xn. And those are going to be our n separate random variables. I'll point out here that we've said that these are independent and identically distributed. So the independent part just means that there's nothing connecting each trial to the next, and so we'll see some of the consequences of that later. The identically distributed part just means they all come from the same distribution, right? So, and that's pretty obvious here because they all point to the Bernoulli trial thing. All right, so that's the setup. Let's have a look at the probability mass function that we're going to be dealing with here for a Bernoulli trial. The probability of getting a success, so we're going to define success as x equals 1 here, is just going to be p. So, some value between 0 and 1. I suppose I should maybe write that in. So p is some value between 0 and 1. Obviously, if it's 0 or 1, you're going to have some pretty boring trials, but technically it can take those values. So we have probability p of getting outcome 1, and we have probability 1 minus p of getting the opposite outcome, because there's only 2 outcomes in this experiment. So we've established our sort of setup and the probability mass function we're working with. So in a sort of setting where you've got a bunch of data, a fairly sensible first step to take is to say, okay, assuming that we know what this variable p is, what its value is, can we figure out the probability of seeing what we have seen? Can we figure out the probability of getting the exact data that we have? And the answer generally is yes. If you've got a probability model and you assume that you know the parameter of that model, you can work out a joint probability of a bunch of independent random variables. So what we have here is a joint probability. if you're familiar with probability, you probably know that our assumption that all of these n random variables are independent means we can rewrite this joint probability as follows. So all we're doing here is we're saying, okay, instead of having one big expression to say, hey, what is the probability that we get, the exact outcomes that we got for all of our n trials, we can split it up and just do a multiplication between each individual thing. A quick note on notation, because we use a very particular kind of notation in statistics, and it can be a little confusing if you're not familiar with it. So we use a capital letter for a random variable to denote an unobserved random variable, or just the concept of a particular random variable in general. A lowercase, usually for the same letter, just to keep things sensible, means it's the observation of that particular random variable. Basically, it's saying, okay, we have data. We don't always want to write the exact value, so we don't want to write, capital X equals 0.01, or capital X equals 0 or 1 in the case of a Bernoulli trial. We don't always want to write the actual numbers there, but we want to have some way of saying, hey, this is the concept of the random variable in general, versus this is the number that we got when we actually observed the random variable. So that's the distinction between these two. And that can come in pretty handy when it comes to sort of like interpreting the very tricky equations that are around. Okay, so I'm going to continue on with calculating this joint probability. And the next line, I'm going to sort of follow on from here. The next line, I'm going to put in the actual PMF, but I'm going to write it in a slightly sort of condensed way, and I'll explain the mathematics of that in a moment. So we're going to write p to the power x1, 1 minus p to the power x2. Oops, sorry, not x2. 1 minus x1. And then p to the power x2, and 1 minus p to the power 1 minus x2. And we're going to do that all the way until we get to xn. And this follows more or less directly from the expression we had before, where we broke up the joint into a bunch of products. So each of these is basically just the PMF of our Bernoulli random variable. Because if you think about it, if x1 takes the value 1, then this part of the term is going to become p, because p to the power 1 is just p. And this part here is going to become 1, because 1 minus 1 is going to give you 0, 1 minus p to the power 0 is going to be 1. And so this whole thing will simplify just down to p if x equals 1, and if x equals 0, then it's going to simplify down to 1 minus p for similar reasons. So this expression behaves the same as our PMF, even though it's written as this sort of product with exponents and stuff. If you're not super comfortable with that, I encourage you to write out the expression and then substitute in x equals 0 or x equals 1 and see how it works out. It should be fairly intuitive once you work through it that way. Okay, so that's the expression for each individual random variable, but we've got n of them, and we're multiplying them all together because they're independent, and so that's how we get to this expression here. Hopefully that's fairly intuitive. Okay, next up, we're going to simplify how we write this a little bit. Some of you might be able to spot how we can do that already, which is we can use product notation. So we can write this as a product from I equals 1 to n of p raised to the power xi, 1 minus p raised to the power 1 minus xi. Hopefully nothing too controversial there. So if you know your exponential laws, then you can probably see what the next step is already, which is that we're going to rewrite this as p raised to the power of the sum of xi from I equals 1 to n times 1 minus p raised to the power of the sum of 1 minus xi from I equals 1 to n. Okay, it's a little bit cramped there, sorry about that, but we'll get back to this equation later with a bit more room. So this exercise might seem a little bit out of the blue so far. We've just got this joint probability that I've sort of roughly motivated by saying, okay, we've got a bunch of data, and assuming we have a model and a parameter, we can calculate how, broadly speaking in a fluffy way, how likely it is that we see this kind of data for a particular value of our probability model. So that's where this expression comes from. Now, something to note here is to calculate this probability, we need to know the value of p, right? That's how we usually do things with probabilities. We assume we know the parameter, and then we calculate what the probability is of seeing a particular data value. But in an experimental setting, we don't know p, we actually want to find p. So there's a little bit of a change in the direction that we go in when we compare statistics, which is what we're doing now, with probability. In probability, we say, hey, this is the setup, what kind of outcomes am I likely to see? In statistics, we say, this is the outcomes we've seen, what's the setup likely to be? And to get around that, or to kind of reflect that, actually, what we do is we take this equation 1, which is a very poorly positioned label for this expression here. We take this equation 1 and we view it as a function of p, because we don't know p, right? Like, the classic thing in algebra is the stuff you don't know, you make it a variable and you let it vary because you don't know what it's going to be. And so in this case, because we don't know p, we view this joint probability as a function of p. And we'll look at that in a little bit more detail in a second. So if we view it as a function of p, we can plot the function, and let's have a quick look at what that looks like. Okay, so the setup here is on the x-axis we've got p, basically. So p can take values between 0 and 1, and on the y-axis we've got that joint probability that we just worked out the expression for. And you might see there's a slider up in the top left there. That slider represents the sum of x. So if we go back to our equation here, this sum of x term, I am representing that with the slider that's called a in the GeoGebra visualization. So let's have a look at what happens to this function, first of all, as we vary p. So we're just looking at what happens as you go from 0 on the x-axis to 1 on the x-axis. And I think it's pretty clear, when you start at p equals 0, the joint probability of seeing the data that we have is 0. Now why is that? Well, we've set a equals 5 here, so that means that we've got 5 heads, or 5 successes. And so the probability of getting 5 successes, if the probability of an individual success is 0, is going to be pretty low, right? It's going to be 0 as a matter of fact. So it makes sense that we start pretty low when p equals 0. And similarly, if p was 1, then we would expect to just see like a whole bunch of successes. But we didn't just see successes, we saw some failures as well. And so that's why the joint probability of seeing 5 successes is very low if you assume that p is 0 or 1. If you allow p to vary, so if you look in the sort of center part of the x-axis between 0 and 1, obviously it changes. And the most likely, a bit of foreshadowing there, but the most likely value for p, according to this plot here, is 0.5, right? And that makes sense. If we get 5 successes out of 10 trials, we would expect that the parameter is about half. Okay, now let's have a look at what happens if I drag this around. So I'm going to drag it over to the side here a little bit. So if we get only 2 successes out of 10 trials, then obviously it's going to feel much more likely that P is low. And that's reflected in this graph. There's a big sort of mass of probability around the sort of lower part of the x-axis near 0. And it's kind of, you can see that the sort of peak of this chart here is at 0.2. And again, that makes a lot of sense because we've got 2 successes out of 10 trials. And as we move this around from side to side, we see that it behaves pretty sensibly. Like if we set it all the way to 0, it's telling us, well, the probability of getting no successes, if we have p equals 0, is pretty high. But the probability of getting no successes if we have p equals 1 is pretty low. That kind of thing. So keep this picture in mind. I'm going to sort of wind it back to the middle there. Keep this picture in mind as we keep talking, because we're going to come back to this function in a bit. So we've spoken about this joint probability of seeing the observed data that we have, and we've plotted that for a Bernoulli random variable where we do 10 trials and we get some number of successes out of that. So let's have a look at what we call the likelihood equation, or the likelihood function. The likelihood function is basically just this joint probability that we worked with after you say, hey, let's make this a function of the parameter instead. So in general, if you have some data that's distributed according to some sort of distribution, and that distribution has a parameter theta, then the likelihood function is a function of theta. And it's basically just saying, okay, what is the joint probability of the data that we have actually seen, assuming that we have the parameter equals theta. Now, you can write this in a lot of different ways, and depending on the problem that you're trying to solve, you might pick a different way of writing it. So if you're focusing on calculating the probability of seeing the data, like if you're focusing on like, hey, what data is more likely given that we have a particular parameter, you might write it like this. And the thinking here is basically you say, okay, what's the probability of seeing this kind of data when we assume that we have this parameter value? But when we're doing statistics, like I said before, what we are actually interested in is the parameter. We don't know what the parameter is, but we do know what the data is. So to sort of be complete, you can write the likelihood function like this, where you say, hey, what's the likelihood given this parameter of seeing this kind of data? And if you're interested in calculating probabilities of data, then you can swap it around. If this doesn't make a huge amount of sense, don't worry about it too much. It's a sort of like a finer point on notation. But the main gist here is just that, like, if you care about the parameter, we're going to write the parameter first, and we're going to talk about the likelihood of this parameter, because that's just a sort of convenient way to talk about it. Something to note here with how I've done the notation is this f. We use f sometimes to sort of generically refer to either the probability mass function or probability density function, but obviously in a particular setting you can use whatever the most appropriate thing is. So in general, if we have a bunch of samples from a particular distribution, we create the likelihood function by finding the joint probability of all of those samples. And if our samples are independent and identically distributed, then we can just take the product of each individual PMF or PDF for those samples. And that's how we kind of come up with that. So we've covered probability models. We've covered this thing we call the likelihood function. So let's next look at maximum, because we've already seen from the visualization that the sort of sensible, intuitive way of estimating the value of the parameter is to just take the maximum value in this likelihood function. So it just so happens that our intuition matches up with where the maximum value is for this likelihood function as a function of the parameter. So let's talk about, okay, if we actually want to estimate the parameter using this idea that, okay, we take the maximum likelihood, how can we go about that? So first, obviously, we start with the likelihood function, and then we just have to find the maximum. As we covered before, the likelihood function for the Bernoulli random variable is p raised to the power sum over xi for I equals 1 to n times 1 minus p raised to the power of the sum from I equals 1 to n of 1 minus xi. Now there's a sort of simplification we can make here where we can write this the same, but the second term we can write as n minus the sum of xi from I equals 1 to n. And the intuition here is just we're going to have this whole sort of expression n times, and if we're going to do 1 minus x1 plus 1 minus x2 plus 1 minus x3, we're going to add 1 together n times, and then we're going to have this sum of all of the x values subtracted from the n. That's basically the intuition there. So, okay, once we have this, we can find the maximum. And one of the ways we can find the maximum is something you've probably covered in high school, which is to differentiate and set the first derivative to 0. Because if you are a little unfamiliar with that idea, if you have a maximum in some function, then at the point where you reach the maximum, it's going to be flat. And if it's flat, then the derivative, so let's say we've got theta on the bottom here, and we've got the likelihood. The derivative at this point here is going to be 0, right? Because it's got a flat gradient at that point, and it has to have a flat gradient to be a maximum, because you go up, and then at some point you stop and you go back down. That's what maximums do. And so if we set the first derivative of the likelihood to 0, then that's one way of finding a maximum. And we can check that, obviously, after we've done the derivative. We can check whether the second derivative is negative. And we'll walk through that now. So first of all, let's find the derivative here. So the derivative of the likelihood function, or little notation error there. So this should be as a function of p, not of theta. Sorry, theta is what we use in general. Obviously, in this case, we're using p. And one more little mistake that I've made is that this should be a partial derivative, because usually your likelihood function has lots of things you can get the derivative of. So we're taking the derivative with respect to p here. So if we take the partial derivative with respect to p, we've got a product of two functions, so we're going to have to use the product rule, and I'm just going to run through it fairly quickly. I'm assuming you're relatively familiar with how to get a derivative. So we're going to get the sum of xi p xi minus 1 so that's the derivative of our first term in the product, and we're going to multiply that just by the other term as it is. And then we have to, do the other part of the product rule. So we have to be a little bit careful here, because we're differentiating with respect to p. So because p is inside the bracket, we have to use the chain rule. So that's going to give us negative n minus the sum of xi I equals 1 to n times 1 minus p n minus some minus 1, and then we multiply by just the other term as it is, so p sum I equals 1 to n of xi. Okay, I'll get rid of this. Okay, if you're unsure about how I got that derivative, first of all, a bit of calculus revision might be helpful. But the second thing is that it actually doesn't have to be this hard. The way I've done it here is a trickier way, and I've shown you how tricky it is. I mean, it's not that tricky, but I've shown you how messy it is. Let's call it messy, because there's an easier way, and there's a nicer way. What we often do in statistics is we work with the log likelihood rather than the likelihood itself. Now, the reason why we work with the log likelihood is mainly because the log is a monotonic function. So if we take the log of the likelihood, the maximum of the log likelihood is going to be in the same place as the maximum of the likelihood. It's just going to kind of shift it a little bit. So if I go back to that diagram I had before, if this is what our likelihood looks like, then the log likelihood is kind of going to shift things a little, right? So if it's a very small positive value, then the log likelihood is going to make it negative. And if it's a sort of larger positive value, then the log likelihood kind of tends to squish them up together. So we might get something that looks like this. But the crucial thing is, with the log likelihood, the maximum is still going to be in the same spot. So again, if you're unsure about why the fact that it's monotonic leads to this behavior, there are probably more detailed explanations out there. So I'm not going to spend too much time on it, but the intuition is basically just that the order of the points, if you're looking at the order of like which one's highest and which one's lowest, that's going to be maintained by any monotonic function, and the log likelihood is going to be a monotonic transformation. So if we take the log likelihood, log of the likelihood with respect to p, what's going to happen? So we all know if you take the log of a thing raised to some power, then the power comes out the front, right? And so what we're going to get is the sum from I equals 1 to n over xi times the log of p. That's going to come from, let me just point this out, that's going to come from this term here. And after that, we're going to have plus n minus the sum over xi times log 1 minus p. So that's just the log likelihood so far. We haven't differentiated yet. But once we differentiate this, you'll see it's a lot easier to work with the differential of the log likelihood than the differential of the just the base likelihood. So we've got our log likelihood. Something I'll just point out here is, for notation, we sometimes write the log as just a lowercase cursive l. The log likelihood as a lowercase cursive l, just to kind of keep things simple and more convenient to write. And once we have the log likelihood, we then differentiate that to find the maximum. So we take partial LP, partial P, and hopefully this is relatively fresh in your memory from whenever the last time is that you did calculus, but the first derivative of log P will just be 1 on P. So we get the sum of xi on P. And then for the second one, the derivative of the log of 1 minus P with respect to 1 minus P is going to be 1 on 1 minus P. But obviously we follow the chain rule, and so it becomes a negative. And so we get minus n minus like so. Again, you can work through the derivation of that yourself if you like. If you couldn't follow it, I know I skipped over some of the steps there, but hopefully it's not too bad. So okay, so that's the first derivative of the log likelihood. Now, to find the maximum likelihood estimate for P, we are going to set this to 0. So we're going to say we want this derivative to be equal to 0. Sometimes people write two little dots there to sort of say, hey, we are making this be 0. And the reason why is for the same reasons that I explained before, that if you have a maximum, then we are looking for the point where the gradient is flat. And so we're going to solve for p, because p is on our x-axis there. So if we set the derivative equal to 0, then we're going to get 0 equals the sum of xi on p, I equals 1 to n, minus n minus all of that, 1 minus p. Now, pretty sort of obvious first step here is to put one term on the other side, but actually I'm not going to do that to begin with. What I'm going to do first is multiply by both p and 1 minus p, so we can get rid of the fractions. What that gives us is 1 minus p times the sum of xi minus p times n minus the sum of xi. So, expanding that out, we get the sum of xi minus p times the sum of xi minus pn plus p times the sum of xi. Now, the eagle-eyed among you have probably already spotted that these guys are going to cancel each other out. And that's very nice for us, because it means we are left with a really nice and simple expression, which is that 0 equals the sum of xi minus pn. And rearranging, we get p equals the sum of xi over n. So this is our estimate. If you recall, when we go back to GeoGebra, if we have a set of coin tosses, we count up how many heads we have, and we get, say, out of 10 coin tosses, we get 4 heads, then our intuition would be that the probability of getting heads is about 0.4. If we follow this maximum likelihood estimate that we just produced, then that's exactly what we're going to get, right? If our number of trials is 10, and the sum of the number of heads we got is 4, then we're going to get our estimate for p as 0.4. So it makes a lot of sense. Obviously, we worked through some pretty tricky sort of mathematics to get here, or maybe not tricky, but at the very least involved, tedious perhaps. But at the end of the day, we got the mathematics to give us the same thing as our intuition would tell us. And that's, generally a pretty positive sign. One final thing to point out here is that once we found the actual estimate, so in the last step of this equation, we replace the p with p hat, just because we want to be really clear where this comes from. We want to be very clear about the fact that, hey, we have estimated p here. We don't actually know what the exact value for p is, because sometimes we want to distinguish between what the sort of conceptual exact value of p is and what the sort of practical estimated value of p is that we've come up with. So that's that. And that really wraps up maximum likelihood estimation for the Bernoulli example. I'm going to do a little bit more on a uniform distribution, just to show you a case where we can't find the maximum using the derivative method.